Hello friends, I welcome you in lecture number 2 on method of separation of variables. In lecture number 1, we have discussed the method of separation of variables for solving homogeneous linear partial differential equations, and we had discussed one example on this method in previous lecture number 1. Today also we are going to solve another first order partial differential equation using the method of separation of variables. And here we have to obtain the solution of this partial differential equation satisfying one condition. Here we are given that find out the solution of this first order partial differential equation which satisfies this condition ux0 equal to 6 times e raised to minus 3x. Here we can observe that we are given partial derivatives of function u with respect to x and t, that is our function required function is function of two variables x and t, and here condition is given at t equal to 0. It is given that at t equal to 0 value of this function is 6 times e raised to minus 3x when t is equal to 0. So we consider this initial condition, and first we will solve this equation using method of separation of variables, and we will have some arbitrary constants in the solution, and we will be able to decide the value of those constants using this initial condition. As we know that in the method of separation of variables, we start by assuming that given partial differential equation has solution in the form of product of two functions of given independent variables. Here independent variables are x and t. So we start with the assumption that this equation has solution in the form capital X times capital T, where capital X is a function of x only and capital T is a function of t only. So this is the assumption which we have made for the solution of given partial differential equation. Now once we assume that solution is in this form, then solution must satisfy given equation. In given equation we have first order partial derivatives of u with respect to x and t. So from this we find out partial derivative of u with respect to x, and we consider capital small t as constant, and capital T is a function of small t, therefore t is considered as constant, and x is a function of x only. So here we write ordinary derivative of capital X with respect to small x, and for this we can use this notation x dash t. Similarly we can write down partial derivative of u with respect to t. For that we consider x as constant, and partial derivative here t is function of t only and we are differentiating with respect to t, so that we write ordinary derivative here, and this is denoted by t dash. So now we can replace del u by del x by x dash t, del u by del t by x t dash in this equation. So suppose we consider del u by del x by x dash t, and 2 times del u by del t plus u. 2 times del u by del t means x times t dash plus u. U is assumed as the product of capital X and capital T. Now we have to separate the variables, or we have to find out the separation for capital X and capital T. So we can observe that in these two terms we have capital T common. So we transfer this term on the left hand side and we take t common, and we have x dash minus x times t equal to 2 times x t dash. Again we can transfer the terms containing capital X on one side. We can take this 2x on this side, and here we have t dash over t. And after this we observe that On this side we have function of only one variable small x, on this side we have function of only one variable t, and these two functions are equal, and this is possible only when both are equal to the same constant, say k. So we will equate both of these quantities to constant k, and we will have two ordinary differential equations of first order, and solving those two ordinary differential equations we will be able to decide these two functions, capital X and capital T. So that work I have done here. I have written this equation first. Given equation is this one. We start with the assumption that equation 1 has solution in this product form. Then we write down del u by del x, del u by del t, and as I explained, because u is solution of given equation, we can substitute del u by del x, del u by del t in equation 1, and we arrive at this equation. Now equation 3 can only be true if each side is equal to the same constant, say k. Therefore I have written k for both of these. After that I compare this with k, and this is equal to k, and here we can take these two on the right hand side, and we divide x dash minus x by capital X, that is x dash over x minus x over x, that is 1, equal to 2 times k. And again I can take this 1 on the right hand side, and I have x dash by x equal to 1 plus 2k. Here I have t dash by t equal to k. This is first order ordinary differential equation, and we can see because we have function of small x here, we can integrate this quantity with respect to x. So if I integrate this x dash over x with respect to x, what I will obtain? I will obtain log of x, and integral of this with respect to x is going to be 1 plus 2k times x, that I have written here. From equation number 4, log x equal to 1 plus 2k times x. Constant is adjusted by writing log of constant, and then we have transferred this log c on left hand side, and now using the property of logarithm, this I can rewrite as log of x by c. This is as it is, and from this I obtain x by c equal to exponential of 1 plus 2k times x, and finally we transfer this constant c on the right hand side. This is the function capital X. In a similar way we have obtained solution of this. If we integrate both sides with respect to small t, we have log t equal to k times small t plus log c dash or some another constant. We have written c dash here, and then we transfer log c dash on left hand side. We have log t minus log c dash equal to k times t. Again using the property of logarithm, this we can rewrite as log of t divided by c dash, and from this t divided by c dash equal to e to the power k times t. Therefore t equal to c dash times e raised to kt. Once we obtain values of x and t, we put them in the assumed solution. Our solution is assumed in the form capital X into t. So we can write that u x t equal to capital X. This is value of capital X. This is value of capital T. Capital X is c times e raised to 1 plus 2k x. That is here, and this is capital T. And we can combine these two constants, c times c dash, and we assume that c times c dash equal to some another constant, say capital A. So A is the arbitrary constant. Now we are interested in the solution of given partial differential equation which satisfies given condition. Given condition is that at t equal to 0, value of function u is 6 times e raised to minus 3x. Therefore, to use this condition, we put t equal to 0 and u equal to that 6 into e raised to minus 3x. What is meaning of this? This means when t equal to 0, value of function u is 6 times e raised to minus 3x. Here capital A is arbitrary constant, and for different values of capital A we will obtain different values of this function u, or we will have different solutions for different values of capital A. Out of those infinite number of solutions, we are interested in that solution which satisfies the condition that at t equal to 0 u is 6 times e raised to minus 3x. So we put t equal to 0 and u equal to 6 times e raised to minus 3x in equation number 8. Left hand side is u is 6 times e raised to minus 3x. Here capital A, this is as it is, e raised to 1 plus 2kx. Here we put t equal to 0 and e raised to 0 is 1. And then we compare these two sides. By comparing, we find that value of capital A is 6, and if we compare coefficient of x in the exponential function, we can observe that 1 plus 2k must be equal to minus 3. So that I have written here. And from this 2k is minus 3 minus 1, that is minus 4, therefore k is minus 2 and value of A is 6. So we have obtained particular values of capital A and k that we substitute again in equation number 8. So therefore uxt equal to, if I take A equal to 6, here I have A equal to 6 and 1 plus 2k is equal to minus 3. So that I have put here. So I will have 6 times e raised to minus 3x into e raised to kt. So that I have written here. And here now I can combine these powers. Base is same e. So I have e raised to minus 3x minus 2t. And taking negative sign common, I can write in the bracket 3x plus 2t. And this solution must satisfy the condition that ux0 is 6 into e raised to minus 3x. Suppose we put t equal to 0 in this solution, then we must have 6 times e raised to minus 3x plus 0. So our solution is correct. It satisfies this initial condition. So this is very easy method, and they generally ask one question on the method of separation of variables in GTU exam. This question was also asked in GTU Winter 2019 exam. So we have discussed the solution of this partial differential equation satisfying this initial condition using the method of separation of variables. All we have to remember is that this method is applicable for homogeneous and linear partial differential equations, and we start with the assumption that solution is always in product form. Number of functions in the product will be equal to number of independent variables in the given equation. Here in given equation we have two independent variables x and t. Therefore our solution is the product of functions of x and t. So here we know in advance the form of the solution. The form of the solution of given PDE is known in advance, or we assume that suppose solution is in this form, and then we try to find out these two functions capital X and t, and for that we put values of these derivatives which we obtain from equation 2 in given equation, and after putting their values we obtain ordinary differential equations in those two independent variables. Here I have two independent variables x and t, so I obtain two ordinary differential equations in variables x and in variable t, and that we can easily solve using the methods of ordinary differential equations. If you are not familiar with ordinary differential equations, then I have uploaded one lecture series on first as well as higher order ordinary differential equations that you can see. Here we have used the method of separation of variables for first order ordinary differential equations to solve these two equations. Both equations are of first order and they are separable, so we can integrate directly. Okay, fine. So this is all about this session. I hope you like it. Thanks for watching.